Good morning, everyone. Good afternoon or good evening, based on which part of the world you are listening this presentation from. What you see is a view from inside of the classic Land Rover Defender. And this is the view from inside of the new Land Rover Defender. Our products today are getting complex. They're becoming smart and they are connected. Thanks to the smart, connected technology and the IoT, organizations are now buried under a flood of data from their products and processes. However, according to IDC, only 0.5% of this data is being utilized. It's not that the rest of the 99.5% of the data is useless, it just isn't accessible to the stakeholders who would find value in it. So, access to the necessary and important data is a challenge in itself. Now, it's equally important to know how these data points or dots are connected. What information does it tell us? On the other hand, our competition is relentless. Tech companies are better placed to leverage the data to deliver the 3E model: engineering excellence, efficient change management, enhanced and differentiated products faster to the market. Digital twin is often thrown at us as a solution, both by the vendors and sometimes the high-level management. Now the question is digital twin a reality today in the context of automotive products, or is it just a buzzword created by vendors? So before we move into the key parts of my presentation, let's try and understand some of the important concepts. Digital twin is often described as a digital replica of the physical entity. It can be divided into three parts: a product twin, which is used to virtually analyze how a product performs under various conditions; a process twin, on the other hand, is used to validate how well a manufacturing process will work; and a performance twin is used as a catalyst for providing efficiency and product improvements. The next concept is Internet of Things, or IoT. It is essentially connecting physical devices or systems to each other via the internet. Think, for example, your home-based internet-connected thermostat and an app on your smartphone. The app enables you to observe and change the temperature in your home from anywhere in the world. Now, let's just scale that up with hundreds of sensors, a sea of data those sensors produce, lots of analytics involved, and what you get is Industrial Internet of Things, the so-called IIoT. Now, if we replace one of the things with the physics or simulation-based digital or virtual model and equivalent physical asset of, for example, a vehicle in this case, what you have is a digital twin. Now, physics-based simulation models have been around for more than 3 decades. They have been used in product development phases of the product lifecycle. Now, they are moving beyond those phases into the entire lifecycle of product by being updated or modified to reflect the ongoing true in-field status of such products, and by being subject to the actual in-field loadings or boundary conditions obtained from these sensors. Digital twin can also be used for monitoring, diagnostics, and prognostics. In other words, digital twin is a robustly validated, time-evolving virtual equivalent of every physical asset in the field. It must enable the user the access to as much of information needed to assess current and future status so that optimal decisions can be made. Now, rest of my presentation is divided into 4 parts. First, I will go through a contextualized definition, why it is necessary and why we cannot have a one twin to rule them all. Next, I will delve into the challenges, the technical and cross-functional challenges that are present to realize the vision. Then, how we can go from vision to value, what guidance is necessary. And finally, we will discuss whether we are asking the right question. So let's go through the contextualized definition and why it is necessary. Now let's take a not so hypothetical scenario into consideration. This is a typical product life cycle divided into 4 key stages. We have 2 customers, one from Wales, another from Russia, having exactly the same failure mode. A damper yoke or body in white is cracked due to peak fatigue loading in the first 3 to 6 months in service, the so-called infant mortality failure mode. Now this could be attributed to anything during the life cycle. It could be the wrong target cascade, could be poor attribute balance. The vehicle may have poor pitch balance, leading to high repeat loading due to long wave pitch roads you often find in Wales or rough roads in Russia. It could be poor communication between the departments, which is again quite common in big companies. Virtual verification processes may not be robust, or they are not correlated, hence the confidence is low, or the validation target may not be chosen correctly. It could be manufacturing variability. It is quite common to have up to 10 or 10 to 15 millimeter of radite variability between the samples, and these 2 samples may be literally sitting on the bump stop, leading to very high peak loads. It could also be because of the environmental factors. The Russian customer may have bought his vehicle during winter, leading to snow or mud backing and hence higher loads. In order to pinpoint where it all went wrong, we need a physics-based simulation model which must be capable of solving multi-physics phenomena in a timely manner. It must also be multi-attribute optimizable, and it must also give us insight on the effect of multi-noise factors at play. As you can imagine, this is quite a challenge. The ultra-high fidelity modeling has been a long-held ambition of many OEMs and suppliers. The first problem is that of multi-scale modeling. This refers to the modeling of behavior of physical phenomena that display dominant behaviors at different length scales. It is also linked closely with physical modeling in different domains and creating interfaces between them. This is the so-called multi-physics modeling. If you solve this problem at subsystem level, then the next challenge is effective subsystem interaction, which is often done via links such as joins. This is another major technical challenge. There is, of course, the gap between hardware capability and software performance. Noise factors. To truly reflect the physical twin in the digital space, we must also understand the effect of real-world noise factors. They all play a major role. System interaction and environmental factors in particular are very challenging. Increasingly, we are using data sent back from, for example, InControl to the newish Cava platform. Whilst this is great, there is no way to add extra channels to this without a torturous or cumbersome processes of changing modules and configurations. Most vehicles are stuck in their version 1 of vehicle architecture, And things only start to ease up with the second generation of vehicle architecture, where some remote reconfiguration is possible via SOTA. It's only in EVA 3 or vehicle architecture 3 that we will be able to get anything like the quantity and frequency of data that's necessary. So, in short, bill of material as maintained to truly reflect the physical asset in the digital space is a challenge. Not to forget, we are talking about millions of vehicles sold by a typical automotive OEM. So I personally don't believe it is currently feasible to have one twin to rule them all. That approach is false. That's why we need a contextual product twin. In the next slide, we will go through the challenges that are involved to realize the vision. No OEM today can deliver a vehicle to the market on its own. Awareness of physical, logical, and functional architecture requirements of the product is key. Roles and responsibilities of servicing and maintaining systems must be clear. That means IP protection and watertight SLAs, less friction in understanding protected and visible content of the twin, and also acceptable format to add and retrieve the data. Lifecycle length of a typical vehicle and software is quite different. There is a high risk that digital content in software formats will become unreadable within few years. Sensor data pose a similar challenge. Locking into the vendor-specific format can be dangerous as companies go bust or they get acquired and merged. Digital twin, in its truest sense or the classical definition, should be avoided for complex products with long life cycles. It is equally important not to forget that digital twin is not equal to 3D model. Insufficiently skilled resource, rigid organizations, and agile by proxy are major impediments, and in reverse order. So in this section, I will go through the guidance that's necessary to bridge the gap between vision and value. Fit for purpose, contextualized product twin must be developed with fail fast, learn fast approach. Business and monetization model should be part of every business case that's presented. A top-down leadership support is absolutely essential. Most importantly, the product twin must be fit for purpose. Aircraft industry versus smart device. A different approach is necessary. One must also concentrate on delivering value all the time. Replace assumptions by facts. How to source the data. Combine digital definition, i.e. bill of material as designed, with the real-world data, that is, bill of material as maintained. Decision of what data to include depends on the overall context. For example, is it an extreme event failure mode like pothole break, or is it a fatigue failure mode? Additional technologies such as augmented data from field, AR devices, people and spaces, i.e. factories, must be taken into account. Then this data must be sorted into product, process, and person and synthesized. That is, data related to use case must be mapped to inform the twin. There is also a need for a setup-based analytics, for example, triggers to automate and direct actions based on the analysis. Could be dispatching a technician for a potential failure mode. There is no doubt that the product twin must be intelligent for predictive maintenance. As I mentioned earlier, it is impossible to capture physics of dynamic systems using simulation model, irrespective of the fidelity. The commonly held belief that usefulness of any predictive model is directly related to its accuracy as measured against the real-world data has been debunked long ago. A more pragmatic approach of using methods of evolving complexity and to perform analysis at each stage of evolution is the right way forward. Unfortunately, it is done all wrong. Hence, the key is to have contextualized product twins. They must be robustly correlated and have quick turnaround time. They must be able to give good enough answer, certainly in the early part of the design cycle, leaving enough room for engineering judgment and experience to play a role. In this final section, we will go through whether we are asking the right question. Vendor-specific and in-house tools to manage simulation and data has created a perfect storm. The team members often sitting in the same department use different tools to provide data to physical test and virtual test teams. This often causes confusion and false positives in one or the other verification strategy. Manual handoffs lead to waste, unmanaged change, and product versions in the simulation process and data management. This is another huge challenge. So this begs the question, do automotive OEMs really need a digital twin in its classic form as it is defined? Or do we need a digital thread, connections to critical information, allowing you to track a product and its digital asset from concept to customer as it is defined in digital thread? So Damien Harty, who is the director of chassis and vehicle dynamics in REE, has sent me this slide, and I quote, "The phrase digital twin seems to mean whatever people want it to mean. It's frequently accompanied by the sort of verbal equivalent of anti-missile flares dispensed by aircraft to offer distraction from the fact that the speaker doesn't really understand the idea." Unquote. So to summarize, if we take the definition of digital twin and try to apply to modern high volume manufacturing, automotive product manufacturing company, we do have multiple and complex challenges. We do not really need a simulation model which is capable of solving multiphysics phenomena in a timely manner, because that's just impossible. We also don't need models which are multi-attribute optimizable, and they certainly cannot cater for the multi-noise factors which are at play. A more pragmatic approach of using methods of evolving complexity to perform analysis at each stage is the right way. What we really need is a contextualized product twin which is robustly validated. It may mean in the early concept stage requirements model or SysML models which are robustly validated. Moving towards design and development, we could have simple 1D models for attribute balance to start with, moving towards the 3D models eventually. Most importantly, these methods must be correlated. At the same time, it's important not to forget that the usefulness of any predictive model is directly related to its accuracy as measured against the real-world data is a myth. It's already been debunked in the technical paper I've mentioned in the references. What we really need is a disciplined digital thread, and what we need is augmented field data for our contextualized product twins. Thank you.